this. And I'm glad I didn't wait any longer, because in the meantime, our 3 missing people haven't shown up. Okay, so, right, I can get that, make it slightly bigger. So now, this is one of the 7 wonders of the modern world, in my opinion. Also, you would be very well advised to, you see this little picture on the left? That's exactly what the transistor looks like. I would advise that you put that on a little chit of paper if you have a sticky note, and then maybe you draw it like this and say the bottom. So that means then if I flip this up, so that means collector, base, emitter. You're just going to lose your mind if you don't have that sitting in front of you all the time. You may even see, some of you may have it taped on one of your breadboards from a previous user. So this is amazing. There's a piece of silicon here and another piece of silicon there, and this is lucite. And it's interesting, he points out that it looks like what a transistor symbol looks like. Over in Bell Labs in Jersey, that's been empty for many years. I don't know. There was this really cool building where it had all this structure and the walls were hanging by supports. Very avant-garde building. I don't know if it's still there anymore. But anyways, yeah, back in the day when there was only one phone company, they had so much money they could set prices to whatever they wanted to. But they funded Bell Labs still exists, but it's not as well funded anymore, and they don't do as much amazing work. But in any event, you see there's the symbols up above, and the bottom line is that you imagine that the transistor is a valve, and you have the handle here, and it's extremely easy to turn. And you imagine you've got a huge high-pressure supply of water above. And so by turning the valve a little bit, you can create very strong output because you can control a large supply. And at the end of the day, transistors are current devices. We'll keep working on that. So you do speak about input voltages, but at the end of the day, it's the current through the base controls the current through the transistor, IC and IE. And just like a diode, if you'll notice the schematic above, the transistor is modeled as 2 diodes together. And it's basically, you have the N, P, N. That means what the charge carriers are. It's not really that important. Also notice though, we're going to be using, NPNs are the ones people use the most. The collector diode is reverse biased, meaning you connect it up above to a positive voltage. We'll see that, but notice the flow down below. It's a little, so you shouldn't really think about a transistor as 2 diodes, other than there are diode drops that you have to worry about once in a while. All right, so it's the only reason to think about a transistor as 2 diodes is only because there's diode drops to worry about. Don't try to analyze a diode by thinking about the direction of what the direction of flow should be. Okay. So when you use a transistor, there's rules of thumb. There's two rules. V collector has to be greater than V emitter, at least by a couple tenths of a volt. It's comparable to a diode drop. And V at the base has to be 0.6 volts greater than V at the emitter, because when you go from the base to the emitter, you're going to have a diode drop. So when you put a voltage at the base, you take that, you subtract 0.6, and you know what the voltage is at the emitter loosely. If there's other things going on that change that, then a transistor won't work. Same thing with VC and VE. You have to maintain those two conditions for the transistor to work. So that will limit a little bit the range of input voltages. It also means that an NPN transistor can only take in positive voltages. Or you can sometimes set it up so it'll accept negative voltages, but you have to add circuitry around it. So if those two conditions are satisfied, then the next two bullet points will be true. Now, when I learned how the transistors, it was by Dr. Coleman, as I mentioned, the Professor G sheet the other day, I think it was, and he taught it by going through all like HFE, you'll notice, or the beta factor, and Horowitz and Hill in engineering, let's avoid math at all costs, say that you never design when with a certain beta in mind. Basically, you always assume beta is equal to about 100. Sometimes people measure 200, sometimes people measure 1,000. But if you always assume beta is no bigger than 100, you're fine. But we're not even going to go that far at first. What we're going to say is, if we satisfy the conditions up there, the current through C is going to be beta times the base, and that's the amplification. But all we can say is the voltage across the BE is 0.6, and the current through the collector equals the current through the emitter. And they will be very close as a rule. So the transistor is a current-controlled valve of current. Okay, what do we got here now? Oh, it's just the same thing. Okay, so this is one of your very first circuits, and it takes a little staring at. He doesn't do a good enough job of explaining it, but it is all there in the textbook. But I'm going to try to make it a little easier. So very conveniently, we see we're applying now. This is all DC at the moment. You generally don't use this with DC, but it helps to learn about how they operate. So I put 5.6 volts here. I get my 0.6 voltage drop, and notice that now the voltage at the emitter is 5 volts. And the power supply is something like plus 12 to plus 15. It can be bigger, but generally, like in a textbook, he uses 15. We're going to use 12 because that's what our breadboard has. So now, how do we calculate the currents? Well, it's kind of weird, but I know that right here is 5 volts, and I have a 5K resistor, emitter resistor. So I equals V base over R, V emitter over R emitter, and it's equal to 5 volts over 5.1K, and for us, that's essentially 1 milliamp. 1 times 10 to the minus 3 amps. So that means then voltage at the collector is going to be, give me a minute, the supply voltage, which is also called VCC, collector. It's just because when they express voltages, there's a tendency to express it with 2 letters. So VE becomes VEE. No, excuse me. That's VCC is the supply. I don't remember the convention. But anyways, the V at the collector, the V supplied, that's the supply, is going to be equal to VCC minus I collector times R of the load. Now, notice the interesting thing here is that in this situation, I collector is a constant. So we can vary the voltage at the collector by changing our load, but the current stays constant. Now we can increase the resistance of the load, but there's a limit because we have to keep VC greater than, in this case, 5 volts plus a few tenths, so say 5.3 volts. So if we increase this load to higher and higher resistances, so the voltage drop gets bigger and bigger, at some point the transistor will shut down. But you can lower the resistance forever. It'll it's the only thing that limits it is how much current can be supplied by the power supply. But because there's only 1 milliamp going through the emitter resistor, almost any power supply can get you 1 milliamp. So you're going to set this circuit something up like this in the beginning, and we're in chapter 4L. And you're going to explore the limits. You're going to put a variable resistor here, and you're going to look at the output, and the behaviors will be explained by these rules, but also the first 2 rules, where you have to maintain those 2 conditions or it won't work. Okay, what's next? Same thing. And yeah, just to advise you to keep this. Notice that the collector diode is reverse bias the whole time. Okay, what's next? Same thing. And this is the first circuit you're going to set up. And I forget where you're going to be measuring. Well, he tells you. He has it set as 20 volts here. Let's take a quick look in here. I thought you'll forgive me. This is from 4N instead of 4L. So, but while I have your attention, I might as well, let's see. So, the first thing you're going to set up is the emitter follower. Okay. Then you're going to measure, right. You're going to do this in 4L.3. all I wanted to say to you here, so you're going to do something like this in 4L.3, and what you're going to do is you're actually going to put an ammeter here between the power supply and this resistor. And I have the variable resistors over there. Okay. Let's go here. So now you can see the beginnings of how it amplifies. And it takes a while for it to sink in, and I wouldn't stress about this just yet. So when we use these things, of course, we send in waves, right? Because we basically want to amplify time varying signals. There's really no reason, as a rule, to amplify a DC signal. It's done, transformer. Well, no, there's things called DC-DC converters, but let's not worry about that for now. So when we wiggle the input, we wiggle the voltage at the base, and the amount of change in the current is dictated by the size of the emitter resistor. So we have, remember, the delta V of the base, is going to equal the delta V of the equals the delta VE. And then the delta I is going to be the delta VE over the emitter resistor. So the smaller we make that, the bigger we make that resistor. What am I doing wrong? It says small RE. Yeah. The smaller we make that resistor, the more gain we get. Or at least we get bigger delta I. Since the output is essentially the drop across RC, delta V equals delta I times RC. So we want a larger resistor at the collector to increase our output voltage. And I'm going to tell you this stuff, but the first thing we're going to work with is an amplifier of gain of 1. It actually has a gain of about 0.9. And you're going to wonder why we're doing such a thing. But this is the basic idea of how you get amplification out of a transistor. So you keep this you keep this in your pocket, and you're going to come back to it. Okay, so here's the very first circuit you're going to make. Notice now that you're going to, instead of to ground, you're going to a negative signal. And remember, when you connect your scope probes, that you measure the output to ground, but this is not ground. Don't ground the negative supply. The reason we do that is that if I put it in this configuration, it won't accept negative voltages here because I won't satisfy the two conditions, right? If I have now a negative voltage here, then I can put negative inputs. say if this is negative 12, if this is negative 4.4, then this becomes negative 5, because I have a 0.6 volt drop. And then I beta, or I base, is going to equal to 7 volts divided by R emitter. But we know that we have a VC. In this case, VC equals the V plus, which is, say, for us, 12 volts. So we can satisfy the conditions, number one, that this is allowed to go below the 0.6 here. So that we got to, if I didn't have a negative voltage down here, this point couldn't go to 5 volts. So I couldn't have the 0.6 volt diode drop. The condition about 12 volts and VC being bigger than VE, that's not a big deal. What would happen there would be if I tried to input a plus 12 volts here, then this would be at 11.4. I would barely make it. And then if I went to 13 volts, the transistor would shut down. But right now we're interested in being able to give it negative voltage, and that's why we give it a negative supply. And you're going to notice that, in fact, the output is going to be lower than the input. And you're going to say to yourself, why do I bother? And the emitter follower, this is one of the very first circuits, simple circuits I learned with. And after I got my master's degree, my boss, my first real job, working with another world famous electronics guy, he showed me this, and he said, here, just take a transistor, wire this up, and now I'm giving you some circuit to test, and now you're guaranteed that you can look at it with your oscilloscope. And it's all about impedances. And so what happens is the emitter follower presents a Z in, a high Z in. So that means that you can have, the higher is Z in, the lower can be Z out of the input source. So let's say you have a source that can produce 5 volts, but it can't produce very much current, which is like a very tiny battery, right? Remember I told you that all batteries are 1.5 volts, but they can only produce a certain amount of current that's dictated by how big they are. And this is where you go back to what I've said earlier in the semester. Always think of, people think of amplification as volts because that's what makes your speakers louder. Higher voltage makes the cone move more, and that's louder music. But ultimately, we're transporting and amplifying power. And power is V times I. And what the emitter follower does is makes I very muscular on the output. So it presents a high Z in, and it presents to the next stage a low Z out. And that's what it does. So it makes you can give it a small signal, and it makes it really robust. It's a very powerful little tool. So you're going to be asked to measure, and then you can see you're going to study clipping, among other things. So you're going to be asked to measure Z in and Z out. And this is where we get back to where I told you also at the beginning of the semester, you have to understand voltage dividers. So what we're doing is, now notice first of all, the original circuit, oh, it's not here. The original circuit calls for a small resistor here when you first get introduced. And that is there because sometimes when you give it an input, something reflects back. And then it'll reflect from the input. So if I have something here, I could end up with something reflecting back and forth, and then it would miss. And that's like when you bring a microphone close to the speaker and it whistles, that it oscillates. So by putting this small resistor here, if there's a reflection, every time there's a reflection, it has to pass through the 270 ohm resistor, and that gives it an IR drop, and it kills it as it goes back and forth. So it cuts out oscillations. So then they're going to ask you to put a 33K in and measure the difference in voltage here. And here's the thing. What they want you to do, and notice there's a 3.3K here. Now let me make sure let me look at my diagram. Right. You imagine that if I put whatever resistor here is Z1, and I measure V out over V in, it's going to be the voltage across Z2, right? That's the standard voltage divider. Now, what they want you to do is they want you to change this resistor here, and if you put 3.3K here, it's going to be about 330K. And what you're doing is you're looking for when the output is 1/2, that means Z1 and Z2 are equal to each other, right? So it turns out Z2 is not 3.3K. Z2 is Z in of the emitter follower. Can everybody see that? Right? Does anybody want me to redraw the diagram? Okay, that's great. I'm so glad you guys got it. So you're measuring it here, and then just make sure there's no phase shift between the two. Because if there's a phase shift, that means that you've encountered your frequency is too high, there's some stray capacitance. Oh, and by the way, you're always supposed to use the 10 times probe. Now, we discovered today, which weirds me out that it took so long, the sinoscopes and the BK precision scopes don't have a 10 times setting. So if you got one of those like Jira and Christian, you have to multiply your volts per box by 10. That's all. But the reason you use the 10 times probe is because if you go to higher frequencies with the 1 times probe, you're not compensated. Remember, the 10 times probe has the capacitive voltage divider, and you just have to use that all the time. So now you're measuring. That's how you measure Z in, and you do something similar to measure Z out. And I'm going to hold off. But what you're going to do is that the Z in is going to it should be equal to beta times RE. So in my example, when I put in a 330K resistor and that means that's the Z in of the emitter follower, you notice that beta is equal to 100. You'll get something different, most likely. This is an idealized example. Now, for Z out, they ask you to put this capacitor here. It's not absolutely essential. And they say to put in and then you put back either the 33K or you put back in the 270. I think you put back in the 33K if I'm not mistaken. Let me see. That's the Z in. I've just been talking a while, so I want to hold off for now. So when we get to that point, if people are totally confused, then I will revisit it, because that's almost an hour of talking. Okay, so I'm going to stop this video.